Mr. Chairman, gentlemen, you see, and ladies. I'm from Opel University of Technology. It is in Poland, very close to Czech Republic and to Germany. First co-author is Dr. Marta Kurek. The plan of presentation, some words about introduction. Next, fatigue strength evaluation, new proposal, fatigue strength scatter analysis, and on the end, conclusion. The termination of the orientation of critical plane is connected with told at the first presentation, Andrea. It is proposed by Andrea Carpinteri and Andrea Spagnoli. So we have special angle alpha. It is sum of two angles. First is angles defined by normal stress. There are typical three possibilities to find the angle of normal stress. I think the most easy is variance method. So when the variance is maximum, it's the critical plane defined by normal stress. It's possible to use for random loading and also for cyclic loading, of course. And here we have special angle proposed by Italian group. So it is from 1, as Andrea told, for cast irons, up to square of 3 if it will be Huber-Mises-Henke equation. So angle, it will be beta from 0 up to 45 degrees. On some conference in Kyoto, the conference organized by Professor Sakane, we told there are many possibilities to define this angle beta. We checked these 4. So if you have from 1 up to the square of 3, this is equation proposed by Italian group. So we thought there are also possibilities other, because this first equation is empirical equation. It's no any physics of this equation. So how we calculate fatigue strength? At the beginning, we have history of normal stress. This normal stress we obtain from bending, and history of shear stress, which obtained from torsion. Next, with determination of orientation of the critical plane angle, as we told, separating for every materials, we need Weller or Baskin curve for pure bending and pure torsion. So, the calculation equivalent stress in cyclic loading, proportional cyclic loading, because at the beginning we want to prepare equations for cyclic loading. It is amplitude equivalent of stress. It will be sum of shear and normal stress with coefficients. It is connected with idea of Professor Maha. He was my boss, as you know. So, from pure bending and pure torsion, we may recalculate it, the coefficient beta and K, where this is divided fatigue limit for bending and torsion. And on the end, from Weller curve for pure bending, we obtain number of cycles. And we decide that this idea of Italian group is correct, but we must find the equation which will be correct, because I'm not sure that this proposed is the best. After calculation and thinking, it's no mathematics find how we find it, but we propose such connection. So it means it will be. Here is fatigue limit for bending divided by torsion, it will be this angle, and here is angle beta from 0 up to 45, as it was. The purpose of Carpentry group, it is this green line from 1 up to square of 3. We see that here it should be cast irons, and milled materials it should be here. But we think, why the maximum it will be a square of 3? This is Huber Mises, we know. But sometimes maybe Tresca it will be correct. If Tresca, it will be 2. For example, we see 10 HNP steel is more than square of 3. It's between square of 3 up to 2. And here we put many materials. We find some materials are from my group, some materials are from German, French, and other from literature. And we see these points. So we see that these points are not correlate with this green line. Maybe this blue line, our proposed, maybe it will be better. But we know that fatigue of materials is statistic problem. So we find that we calculated for bending and torsion, the combination of bending or torsion for material, we calculated for every beta angle, we calculated lifetime, and here it is the scatter. When the scatter is the minimum, this is optimization of angle beta. But as I told in the statistic, and we decided that the range is T minimum up to 1.1. So the angle beta is from beta minimum up to beta maximum. So for example, for this GTS 45 materials, we obtain beta, that scatter band is minimum, beta is 20. But we see that the scatter band for large regime is very flat. In practice, it's flat. So in practice, it is possible from 8 up to 45 for this material. And the same, we obtain Weyl curves for bending and torsion, and we obtain sigma AF divided by tau AF. But in practice, it's no line. It is some scatter. We decide this is scatter minus 5% plus 5%. So we have this point. So for this material, this point is the best possibilities, but the range of scatter is this. So we will see that Italian propose and our propose is in this scatter is connected with these two lines. So I come back to the first fissures. So we put the scatter for some materials. You see, 1 second, next, this material doesn't correlate. It's from the Ishihara Kawamoto material. Our aluminum alloy, next, doesn't correlate. This is very well. Doesn't correlate. So we have the scatters. We see that for some materials, the scatter is very flat. So if it is very flat, for example, you see this yellow, it is copper. In practice, in every place are possibilities. So, on the end conclusion, the following conclusion can be drawn. The proposed motor has been developed on the basis of relation of material in elastic brittle state, Galileo's hypothesis, and in elastoplastic Huber-Mises-Henke hypothesis. These states are nevertheless not limited, like in the case of the Carpentry model. The proposed model accounts for a wider range of the ratio of normal to shear stresses than Carpentry model. The presented analysis is in this step for the verification of the foundation of effectiveness of the new models, taking into consideration the scatter of the termination beta angle and also the ratio of the fatigue limits for bending and torsion. It may be noted that most of materials coincide with the proposed material. In the future, more materials should be analyzed in order to continue the verification of proposed model or to look for an even better suited model for experimental test. This 5-point Marta Kurek started work for more materials, because now we have 10, we must find more materials. So thank you for your attention.